Okay, I think we can get started. Hello, and thanks for having me here today. So my name is Andreas, and I'm with the Samsung Ghost team, which is the global open source team, and we have a fancy penguin as our logo. So I'm really happy about that one. I'm not sure what it's in. It's like in the ether. So this, I've been doing some work in Ublk as a side project, and I thought it would be cool to share some of the stuff that I've learned about Ublk, and that's what I'm going to do in this talk. So if you're already familiar with Uring and Ublk and zone storage, you can check your emails. Otherwise, this is for you to get an overview of the technology in those components in that project. So I'm gonna go over zone storage really fast, a little bit on I/O Uring because that's the transport that Ublk is relying on, and then I'm gonna talk about the architecture of Ublk, and then finally about some of the work that I did in Ublk, which is adding zone storage support to Ublk. And if you have any questions, feel free to stop me, and if I don't see your hand, make a noise, and don't necessarily save the questions for last. So zone storage. So zone storage in Linux is a storage abstraction where we divide the LBA space of a block device into a number of zones. And within each of these zones, we have to write the data sequentially. And we have to write it at the write pointer. So when we write data to this zone, we move the write pointer forward, and the write pointer is always pointing to the next place where we have to write. In order to erase stuff, to be able to rewrite the zone, we have to reset the zone. That discards the data that we have in the zone and puts the write pointer back to the beginning of the zone. And the zones are, the capacity of a zone is the amount of space that we are able to write in the zone, but the actual size of the zone might be larger. So we can have some space in the zone that's not writable. And we also have the option of appending data to a zone. So we can tell the device, take this chunk of data and put it at the write pointer wherever that is. And then the block layer or the device will return to us the place that it actually put the data. So this interface is put in place in order to support a singled magnetic, SMR singled magnetic something, where you have the SMR recording. So you have the traditional drives are spinning platters of Rust, where we write the data as tracks on the platters. And in order to squeeze more data into the hard drive, we can sort of layer the tracks on top of one another. And that the consequence of that is that we have to write each of these zones sequentially. But the abstraction is also really well suited for flash media because the actual physics of flash media requires us to write the media sequentially. And in normal SSDs, we have a translation layer that takes our random access interface to the media and translates it into sequential writes for the underlying media. And by exposing this the actual physical characteristics of the media to the applications, we can gain some benefits in efficiency and performance. So that is why we have this. So the devices in Linux appear as normal block devices. You read and write them the way you read and write traditional devices, but you have to write at the write pointer or your I/O may fail. And if you read beyond the write pointer, depending on what kind of device and the settings of that device, you will either I don't know if you can get a failure, but I know that you can get pattern data if you read beyond the actual write pointer. In order the zones of these devices, it has a state machine that describes the state of the zone. All of the details is not important for this talk. But one of the things that we can do to a zone is we can reset it, or we can finish it, like to finalize it and say, now we're not going to write any more data to it. But in Linux, we also have the option of getting enumerating all the zones and getting some information about the state of the zone, like where's the write pointer and what is the state of the zone? Is it open or closed or whatever? And the last one, we cannot zone append from user space, except that we can through one of multiple interfaces. For instance, for NVMe, we can do it through ioctl pass-through or through IO-Uring pass-through. And I think actually also, as I stand here, I think about we can do the ZoneFS, which is a pseudo file system that will expose the zones as a file system, and you can append through that as well, but not through normal I/O operations. I'm going to give a quick overview of IO-Uring because that's the method for communication used in Ublk. So IO-Uring is it's a kernel. It's a means for user space to communicate with the kernel that uses ring buffers. So you can basically put commands into the ring buffers, and the commands can be stuff that you would normally use system calls for. So open, close, read, write, rename directory files, stuff like that. You can put those into ring buffers, and you can queue a number of these, and then you can enter the kernel, and the kernel will handle all of your commands in your queue. And one of the reasons to do this is you can save some cycles by doing more work for each time you enter the kernel. And IO-Uring it's a huge system with a lot of tunable parameters. And I was able to borrow this figure from a guy named Jakub, who wrote a nice blog post about the worker thread pooling mechanism in Ublk. So if you're interested in that stuff, I would suggest you go read that. It's a good blog post. So this is a picture of IO-Uring as seen by the kernel. On the left side, we have the submission queue, and on the right side, we have the completion queue. And those two are ring buffers. So when user space wants to get some work done, he puts in entries into the submission queue, and one of the fields in the submission entry is like what kind of work do we want done. It could be like accept a socket connection or something. The kernel will then pop these submission queue entries and create an internal request structure that will propagate along this middle line, and the kernel will try to complete it in line if possible, like immediately, and put the result back into the completion queue, where user space can then pop the result from. So we also have the option of spinning up a thread at the far left of this figure, so the kernel can pull the ring instead of waiting for user space to trap into the kernel, and that helps us in it saves us all of the trouble we have when we enter the kernel. There's a lot of mitigations for the speculative execution vulnerabilities that you can sort of sacrifice a core pulling this, and then you don't have to enter the kernel all the time and lose all of your cache state and all that. So IO-Uring will try to complete the IO inline. If that's not possible, if it gets like a -e again from whatever IO it's doing, it will try to put the request into a pull set, and the pull sets are pulled when user space enter the kernel or by this pull thread. If that's not possible, IO-Uring will spin up a thread, and it has like a thread pool, and it will spin up a thread and basically issue the IO blockingly on that thread. And so from this blog post, one of the things that the guy concludes is like, if you do a UDP accept, that will usually fail with again if you try to do it async. And the kernel will actually spin up a thread for each accept you do. So if you have a queue depth of like 4K and you submit 4K accepts, the kernel will just spin up 4K threads. So there's many ways that you can like tune this, but that's the default thing it will do. One of the commands that was added to IOUring recently is the IOUring command pass-through, which you can, if you're building a kernel driver, you can create a file, like I'm not sure what you call it, like a file descriptor, and if you populate the Uring command in the file operation struct, then you can have this Uring command hook into this file descriptor, and this means you can instead of, if you have something like ioctls where you would normally as a way of implement like custom syscalls for your device. Those are blocking and relatively slow because you have to like trap into the kernel and do your thing and then back to user space, and you have to, in user space, the thread will be blocked while you wait for the actual to finish. Now you can actually just queue a Uring command in a Uring and then go do something else, and when that one comes back, you can get the result. And that is what Ublk does for the I/O. So that was a little Uring primer, and now for the Ublk. So Ublk allows for the implementation of block devices in user space. A little bit like Fuse allows for file systems in user space, but then it's just block devices. Ublk it's a block MQ driver, and it uses a program that you're running in user space that actually will do the I/O for you. So here is a figure that I like to pull up when I'm talking about the Linux storage stack. I was informed earlier today that this is old and outdated, but I still think it serves a nice purpose. Someone told me I needed a lot of like back arrows on it. Yeah. Anyhow, I think it's like for like a high helicopter overview, it's absolutely fine. Up top, we have user space submitting I/O into the kernel via one of many interfaces. We have this the per core software queues where we can do reordering and splits and quality of service and stuff like that. And we then have some hardware dispatch queues for which there may be fewer than the number of cores. And at the bottom we have the block MQ device drivers, which is where, let's see if I have a cursor. This is where Ublk lives. So it hooks into these hardware queues and it issues I/O down below. So this is, let's see, this is an attempt to display the Ublk architecture. To the left, we have the hardware queue where the kernel will hand off I/O requests to the driver. So this figure is a per core. Like you would instantiate this for each core that you're running the block device on. So all of the data structures are thread like local to the core. The kernel is handing off IOs over here, where you see you have this the queue with the request and the arrows, and okay. Actually, let's start at the user space side, because that actually has to come up before the kernel can issue IOs. So Ublk will spin up a worker thread, and that worker thread will create an IOUring instance where the depth of the queues match the number of tags or the queue depth that you have in the hardware queues. And it will basically, for each slot in this queue, it will submit a fetch command, and that fetch command will hang until there is I/O from the kernel. And at that point, you have I/O coming in from in the queue request, and that function will go in and complete the during I/O that corresponds to the tag that you have in the request. So if you are not familiar with the tags, each I/O in the storage stack for a device has a unique tag. So if you have a queue depth of 4K, you will have 4K tags. So you complete this I/O during command request for the corresponding tag. Ublk worker wakes up and goes like, okay, I have something to do. So, but the during is sort of flipped because the completion means that you have work to do. Because the completion entries are not particularly large, we use a shared buffer on the side to be able to describe the work that we want done. That could be like read or write or discard or whatever. So Ublk worker goes and fetches the I/O descriptor matching the tag, does the I/O however it wants. It could be like opening a network connection or opening a QCOV2, something like that. And then when it's done, when it has done the I/O, it will submit this fetch complete command through the submission queue, and that will have the result of the command. And it will block until there is again more I/O to be issued for that tag. I hope that makes sense. Okay, so now the stuff that I actually did, the zone storage support. So I told you interact with the zone storage devices via ioctls. And the way that most of the zone storage ioctls are implemented is in the block layer. So now I have here the block dev common ioctl will actually turn this ioctl into a request and inject it into the block MQ stack. And that will eventually reach the device that we are targeting, and the device will handle it. So for all of the operations, the zone storage operations that work like this, adding zone storage support is basically adding 2 lines in the queue request function. Just, okay, if you see this kind of request coming in, use this new ublk command, and then in user space you handle it however you want. But for the report zones, ioctl is implemented differently, and I'm really curious as to why. I have no idea why this is. If someone knows, maybe you can tell me later. But instead of the block layer turning the ioctl into a request, each driver will have to populate the report zones function pointer in the block device operations vtable. And it will have to construct the zone report somehow in there. But the fact is that, Matthias? So I looked at like 3 different implementations, and they are like almost identical. But like, so like NVMe and Verdio block, and now at least Ublk, like I think the functions are so identical that they probably could be like extracted and put somewhere else, refactored even maybe. But to me it was super annoying because that meant I have to write actual code. So the way that I looked at the Verdio block and NVMe and the way they handle the problem is in the driver they convert this ioctl into a pass-through request, this regup driver in that is able to just pass through a command to the device. And then inject that into the block MQ, allocate a tag and inject it into the storage stack, and then block for it and wait for it to return. And that meant a little bit more work, but I managed to get it working. And the patches are available, and you can go have a look if you want. Someone really wanted Zoneappend in it, which I didn't implement, but I will soon. and then I'm going to resubmit that. Hmm? No, I do plan to do it, but this is a side thing for me, so I have to, yeah, do it at night, basically, right? And there is more. I managed to put Rust into this talk as well. Because so I wrote a pure Rust implementation of the user space Ublk daemon. I wrote it on the plane home from LSF, so it's like a bit rough. I will put it online as soon as legal says, okay, you can put it online. And if you want to join that, you can reach out to me, and there's plenty of work to do in that on that project. There are a number of other implementations for the user side for the user space side of things. The Ublk server that Ming wrote, Ming also is the maintainer of the Ublk driver, and he wrote a user space component to go with it. It's in C++20 with coroutines. I had to look a lot in the C++ documentation to work with it. And there's also a library, libublk, that you can use to implement user space components. And then there is a smaller version of the user space component in the block tests. There is also an implementation in SPDK that allows you to attach SPDK block devices into the kernel, so they appear as normal block devices, which is really cool. And then there is a Rust binding, raw Rust bindings for libublk as well, but nothing pure Rust until this. Any questions? No? So that's up to you to decide. I just provide the tools. No, so you can do anything you want in user space. You're not encumbered by license or kernel maintainers telling you what language to use or anything like that. And also, like if you're doing, let's say you're doing research on a device mapper or something, you can move a bit faster in user space if you want to try things out. In kernel space, everything is, in my opinion, a little more difficult. And when you move to upstream stuff, it's even more difficult.
Something similar like libUSB versus USB drivers in kernel space.
If that is like USB stack in user space, then yes.
It's not like NVMe in user space or network drivers in user space. For performance reasons, it's not like that.
There is a performance penalty by doing it this way. It's relatively low. And it's primarily caused by the whole chain is not zero copy. There is one copying of data, but I know Ming is working really hard on making the entire thing from user space into the kernel and back out to user space zero copy. And I think then the performance penalty will not be as bad. So I don't have any numbers with me today, unfortunately.
It adds with. I think when we get away from I get a zero copy, I think it's just like a microsecond of latency per I/O.
Which is a lot, but with high queue depth, you can live with it.
Depends on the size of your I/O, and right, you can compensate by doing clever things in user space, adding your magic sauce. Yep. So you can do like things that are really hard to do in kernel space, like doing deduplication using really fancy algorithms, proprietary compression algorithms, and things that you can experiment a lot and figure out what would work, and then maybe implement it in actual hardware, or maybe get it into the kernel.
I mean, there's also like you can use whatever dependencies you want. You're not like you can't get any kind of dependency into the kernel. So if you want to connect to network attached stuff, I know, like, if you want to do TLS for like TLS handshake, it's still in user space, so you don't have these problems if you go and implement your stuff in user
Yeah,
space.
they're moving network, or implementing at least network block devices in user space, loopback and like QCOW and like all these things that are easy to hack in user space. Is a good sort of target for Ublk. And this is just wiring up some storage support for that. So Ublk has been in the kernel since
It's not that long.
No, since
like
the
a
fall,
year
right?
or
So
so.
it's like a little more than half a year. So
Cheers.
yeah, we similar like with Uring and yeah.
But that goes more towards Fuse, right?
I mean, sorry for sidetracking it, but that whole FileSystem discussion was bullshit. I mean, the reason why they are problematic is because no one maintains them by saying we move them to user space by completely rewriting them to make them easier to maintain. Fundamentally does not solve that problem. But sorry, this was just a little bit off topic. I had to throw that in. As for, I mean, there's a lot of things people do right now with doing, like, especially NDB or other network storage to the local system to implement crazy, wacky value add they might not want to share or that are too scary to do. And I mean, for any of those, switching to Ublk is going to be an instant magic improvement without a lot of effort. And I mean, in terms of performance overhead, it really depends on what performance you're measuring. I mean, if you're accessing a slow disk or like a remote network, you probably won't notice it except for the memory copy overhead. If you're trying to get the latest performance out of a high-end SSD or one of the last Optanes, it looks different.
For sure. the very last. Okay, thanks.